Hello, welcome back to EEE 101. Today we will talk about source transformation theorem. Let us consider an ideal voltage source first. The voltage across the source is V, the current through the source is I, and the value of the voltage source is Vs. The equation that describes the IV relationship for this ideal voltage source is V equal to Vs. That is, the voltage does not depend on the current flowing through the voltage source. Now let us look at a current source Is. Again, V is the voltage across the source, I is the current through the source, and the IV relationship for this ideal source is that I equal to Is. In other words, the current of this source does not depend on the voltage across the source. Let us now try to show these two equations graphically. We want to draw a graph where the x-axis represents the current I and the y-axis represents the voltage V. V equal to Vs means y equal to constant. This is a straight line which is parallel to the x-axis. So for the ideal voltage source, we get this straight line where the voltage is constant at Vs, and this straight line tells us that no matter what the current is, voltage is fixed. Now let us look at the equation for the ideal current source. I equal to Is means x equal to constant. So that is a straight line parallel to the y-axis, which is represented like this. The straight line tells us no matter what the voltage is, the value of the current is fixed at Is. From these two graphs, we see that the characteristics of the ideal voltage source and the characteristics of the ideal current source are normal to each other, which implies that the ideal voltage source is in no way equivalent to ideal current source, and it is not possible to transform an ideal voltage source into an ideal current source. Source transformation theorem does not tell us that. Okay, so what does the source transformation theorem tells us? To know that, let's proceed a little further. We consider an ideal voltage source Vs in series with a resistance Rs, and we are interested in the terminal characteristics of this combination, that is the relationship between V and I at the terminal of this series combination. Writing KVL, we can write V is equal to Vs minus Rsi. In this case, we see that the terminal voltage V does depend on the current I. This voltage V is not independent of the current I. Now let us consider another possibility where we have an ideal current source Is in parallel with a resistance Rp. Again, we are interested in the terminal IV characteristics of this parallel combination. That is, what is the voltage V and the current I across its terminals. Using KCL, we can see that the current flowing through Rp in the downward direction is Is minus I. So using Ohm's law, we can see that the voltage V is Is minus I multiplied by Rp. If we multiply the bracket out, it becomes Rpis minus Rpi. So both equations, the voltage V depends on the current I. And these are equations of straight line which may be represented by y equal to mx plus c form. Okay, now we want to draw these straight lines for the ideal voltage source in series with a resistance. Vs is equal to C and minus Rs equal to M. So for zero current, the voltage will be Vs, and as the current increases, the voltage V will decrease. This is given by this straight line. C is the y-intercept of the graph, which is Vs, and the slope is minus Rs. Now let us look at the equation for the parallel combination of current source and resistance. In this case, the constant term C is RPIS and the slope is minus RP. So again, for zero current, V is equal to RPIS, and when the current increases because of the negative sign, the voltage decreases. So if we draw the graph, it looks like this. C is RPIS and the slope is minus RP. From the graph, we see that now both IV characteristics are similar. They have a constant value for zero current, and as the current increases, the voltage decreases linearly. The two straight lines are equivalent when both the straight lines have same value of C and same value of M. So if I compare these two straight lines, we can say if Vs is equal to RPIS and if Rs equal to Rp, the two straight lines will be equivalent. Having this knowledge, now we can say that it is possible to transform an ideal voltage source in series with a resistance into an ideal current source in parallel with a resistance. So this is where the source transformation theorem comes into play. It does not transform an ideal voltage source into an ideal current source or vice versa. Rather, it represents a transformation between an ideal voltage source in series with a resistance and an ideal current source in parallel with a resistance. The transformation can work in both directions. If we go from voltage source to current source, then we know the value of Vs and we know the value of Rs. We want to find out the value of equivalent Is and Rp. Using what we have discussed in the previous slide, Is is equal to Vs divided by Rs as shown here, and Rp is equal to Rs. So using these two relationships, we can transform the voltage source and a series resistance into a current source and a parallel resistance. It is also possible to do the transformation in the opposite direction. Now we have a current source in parallel with a resistance. That means the value of Is and Rp are known. We want to transform it into an equivalent voltage source and series resistance. We want to know Vs and Rs. Again, using the same knowledge, we can say Rs and Rp are equal and Vs is equal to Is Rp. So these two relationships, transforming from left to right or from right to left, these two relationships are collectively known as the source transformation theorem. Remember that source transformation theorem applies to both independent sources as well as dependent sources. If we start with a dependent voltage source and transform from left to right, we will end up with a dependent current source. If we start with a dependent current source and transform towards left, we will end up with a dependent voltage source. Remember that transforming a dependent voltage source, you will not get an independent current source and vice versa. There is another subtle point that we should be aware of. When we make the transformation from this voltage source and series resistance into the current source and the parallel resistance, where will be the arrowhead? What will be the direction of the current source? Or if we go in the opposite direction, where will be the plus of the voltage, or what will be the polarity of the voltage source? By comparing these two diagrams, we can see that the node towards which the plus of the voltage is also the node towards which the arrow of head of the current source remains. So if we make the transformation, the arrowhead should be towards the node which had the voltage source. Going in the opposite direction, the plus of the voltage source should be towards the node which has the arrowhead of the current source. If we remember this, then After the transformation, we will always get the right polarity or the right direction. Okay, now we know source transformation theorem. Let's apply it to solve a circuit. In this circuit, we want to calculate the power of the 6-volt source using successive source transformation. Successive means we will transform source sequentially one after the other until the circuit is simplified. If we inspect this circuit, we observe that no two resistance in this circuit are in series and no two resistance in this circuit is in parallel. So it is not possible to simplify the circuit by using series parallel combination. In such cases, source transformation is an alternate approach to simplify the circuit. Source transformation can be applied when we have a voltage source in series or a current source in parallel. In this case, we have two voltage sources and both have series resistances. This is one case and this is the other case. Theoretically, we can transform both, but specifically which one should be beneficial for us will depend on what the question tells us to do. In this case, the question tells us to calculate the power of the 6-volt source. If we make this transformation, the 6-volt source will disappear. So we don't want to transform 6-volt source in series with 4 ohms. We want to keep it as it is. Let's transform 40-volt voltage source in series with 5 ohms resistance. Remember that this series combination is between node B and node C. So after the transformation, the parallel current source and resistance will be also between node B and node C. It is important to keep track of the nodes correctly when we are making source transformation. Okay, so after we make this transformation between node B and node C, we will have 5 ohms resistance in parallel with a current source whose value is 40 volts divided by 5 ohms, that is 8 ampere. And the arrowhead of the current source is towards node B because the plus of the voltage source is also towards node B. So the current source has been drawn with the correct polarity. I have not drawn the complete circuit because I am only interested between node B and C and I am not doing any change in the rest of the circuit. So I only drew the part of the circuit where changes are being made. In our original circuit, we did not have two resistances in series or in parallel. But after the transformation, we can see 20 ohms and 5 ohms appear in parallel. We can combine them and the parallel combination of these two resistance is 4 ohms. So this circuit simplifies to this circuit, 4 ohms in parallel with 8 ampere current source. Now let's look also between node A and C, 16 ohms and 30 ohms. So if we zoom out a little, we get this circuit. Again, here I have not drawn the complete circuit. What is on the left of node A is left out. In this circuit, between node B and node C, we see a resistance of 4 ohms in parallel with 8 ampere current source. So we can make source transformation, that is, these two can be replaced by a voltage source in series with a resistor. The resistance value is 4 ohms, which is equal to Rp, and the voltage source value will be IPRP, that is 32 volts. So after the transformation, this is the circuit we get. Again, notice the plus of the voltage source. The plus is towards node B because the arrowhead of the current source is towards node B. After this transformation, we find that the 16 ohms and 4 ohms are in parallel with one another. We can combine them in series to get 20 ohms. And when we make this combination, node B vanishes. When node B vanishes, this 20 ohms in series with 32 volts appear between node A and node C. We can make source transformation again. And when we do that, this 20 ohms appear between node A and C, and the parallel current source also appear between node A and C. The value of the current source is 32 volts divided by 20 ohms, which is 1.6 ampere. 20 ohms and 30 ohms are in parallel. If we combine them in parallel, we get 12 ohms. So this is the circuit after this round of simplification. Node B has vanished. We have only node A and C here. Okay. If necessary, we can transform this parallel combination of 12 ohms and 1.6 ampere again into a voltage source in series with a resistance. If we do that, this is the circuit we get. On the right hand side, we have 12 volts and the voltage source is 19.2 volts because this is 12 times 1.6. And the plus of the voltage source is towards node A because the arrowhead of the current source was towards node A also. And on the left hand side, this is my part of the original circuit. We have our desired 6 volt source in series with 4 ohms. 12 ohms and 4 ohms are in series. So we simplify the circuit in this simple series circuit with one loop. Our original circuit was a 3-loop circuit, and we have applied source transformation 4 times. After 4 times, we have been able to simplify the circuit into a series circuit. In a series circuit, the current is the same. Let's say the current is flowing in the counterclockwise direction with value I. We need the current because our question tells us to calculate the power of the 6 volt source. The voltage is known. If I know the current, I can calculate the power. We can write KVL, and when writing KVL, we typically go along the direction of the current. So now we are writing KVL by going in the counterclockwise direction. The KVL comes in this form. Here we have only one unknown I and one equation. So I can be calculated as 0.825 ampere. Okay. Then the power of the 6 volt is plus 6i because I and this 6 volt source satisfy passive sign convention, and we get the result. So in this circuit, we see how using source transformation theorem repeatedly allows us to simplify a circuit which could not be simplified by rules of series and parallel resistance combination. That is the advantage of source transformation theorem. That is all for today. Thank you.